Hi folks, thanks for joining me in this honors geometry video for section 6.3, which is using similar polygons. I want to start off this section by talking about the notion of similarity in terms of how it compares to congruence. So if I were to ask you, is this red triangle congruent to this golden one? I don't know if it's obvious just by looking at it, but I imagine what you would do, having come this far in the course, is try to figure out if the sides that correspond and the angles that correspond are the same. Maybe if we had only pieces of information, we could use like a shortcut like SSS or something, but one way to do it is to kind of see how this one compares to the yellow one by dragging them on top of each other, and then no, clearly they're not congruent because the golden one is much bigger. The side lengths are longer, so we have the opposite of SSS. We have anti-SSS. So it's not even I don't know, it's a hard no with these two things being congruent. But there is some notion of how they relate to each other that's more than just two random triangles. It kind of looks like this red one is a shrunken version of the gold one, and it kind of looks like if I keep the same sides like of the same proportion and scale the shape up proportionally, well then it looks more like they could be congruent to each other. So it's not that they're not congruent because they're two random triangles, it's that they're not congruent because the red one's a shrunken version of the gold one, or conversely, the golden one is a blown up version of the red one. So we have a name for this. It's not congruence between the polygons that we have, but it's something called similarity, which, as you can imagine, is a slight extension of congruence, where instead of the sides being congruent, there's something else about them. What we should have noticed between the red triangle and the golden triangle on the previous page is that the angles were the same, no matter what. When I blew up the shape or shrunk it, it was still the case that the corresponding angle pairs, all three of the pairs, were congruent to each other. We wouldn't expect this to change if I were to, like, for instance, double the sides of a triangle, because I wouldn't have to therefore double the angles as well. That would make their sum 360 degrees instead of 180. We know that that's not how triangles work. So if I have two polygons that are similar, like the ones on the previous page, what we're going to have is congruent corresponding angles, same as with congruent triangles, but then also proportional corresponding sides. So there was some scale factor where I must have blown up one triangle proportionally, all of the sides of the same proportion, by multiplying by something or dividing by something that gives me the relationship between the red and the gold. When we define this as similarity, we should note that the angles are congruent, the angle pairs are congruent, the ones that correspond, and the sides are proportional. So what do I mean by that? If I have these two shapes, which are, as you can see, they're similar, what it looks like is this little guy on the right, polygon geome, is like a shrunken and kind of reflected version of polygon rules. Definitely no subliminal message here. And what that would mean about the corresponding angles, like, it looks like R corresponds with G, is that R and G are congruent to each other. Again, same as when we had congruent polygons. I could do the same thing with all the other letters in this congruent statement, like O corresponds to L, so L is the 4-arc one, O is the 4-arc one, so they're congruent to each other. Same as when we were dealing with congruent polygons, but with similarity, what we should note is that these side lengths on the now red polygon, the ratio of those to their corresponding sides from these is going to be the same if I were to choose any red side to its ratio to any green side. So for instance, I can kind of look at, I could set up proportions. If I'm dealing with ratios, what we talked about in section 6.2 and 6.1 even, was ways that we could establish ratios, or proportions rather, where we can say this ratio is equal to this one, and then we can solve. So for instance, EG is the first two letters of the left polygon, RU is the first two letters of the right one. So what I can kind of say here is that every ratio that I take from red polygon to green polygon is going to be of the same proportion. Suppose the red one was twice as big, like the side lengths are double that of the green polygon. Well, then every ratio that I create between the corresponding sides here, every ratio of red side to green side is going to be 2 to 1. I don't know what the actual ratio is on these things, but what I do know is that if I were to take like RU over EG, or like LU over EO or OE, those ratios are all going to be something, like bigger number over smaller number, because I'm starting with the bigger polygon first. So you can imagine that if I know that two polygons are similar, I can set up some proportions, and this will allow me to solve for unknown sides, provided I have the other ingredients that let me do so. Just to be clear on something like this, if I have similar triangles, which yes is a big deal, I've been kind of amping up to this as a precursor to trigonometry for a while. What it would mean for, and if we were in class, I'd have you spell these out for me, but what it would mean for these two polygons to be similar, we could deduce from this similarity statement that, for example, A and R are congruent to each other, B and that corresponds with S. And then, even without knowing that they're similar, we still know the third angle theorem would tell us this, that T is congruent to C. And then again, furthermore, if I want to look at corresponding sides, AB is the first two letters, RS is the first two letters. So AB, ooh, that's shaky, corresponds with RS. So the ratio of AB to RS is the same ratio as any other two sides that correspond, provided that I'm starting with triangle ABC in the numerator. Because I'm essentially looking at the ratio of big triangle to small triangle. So being consistent with this is important. I also could have looked at different permutations of this. Like, I could have looked at, via some of the theorems and, like, conjectures that we had in the previous section, I could have looked at the ratio of, like, ST to TR. That seems to be the same as the ratio of BC to CA. And I could take this proportion right here and just kind of, like, snip out one of the fractions and then play with the pieces to manipulate it algebraically to get something like that. But this is essentially the set of proportions that we want to set up for a problem like this. So here's an instance where we actually want to solve for stuff, and what we're going to have to use is a scale factor. A scale factor is a ratio of lengths with corresponding sides of similar polygons. And the order in which I do this is important. Here I note that it's going to be the first to the second. I could look at ratios as like 3 to 7 or something like that. But the order in which I present these things actually matters, kind of like a fraction. Like, a numerator to denominator is not the same as the reciprocal of the thing, right? And I kind of need to be able to specify what the first term in the ratio represents, like which polygon it represents, because that'll tell me which one of these is bigger and which one is smaller, as though it wasn't obvious by looking at it anyway. But let's see. We want to solve for x. We also want to find the scale factor from math to you love. Again, no way there's subliminal messages here. But what I should note is that because these two things are similar to each other, because these two seemingly trapezoids are similar to each other, it means that corresponding sides are going to be proportional. And that a lot of the features of one of these shapes is going to be captured in the other one. For instance, we have what appears to be a isosceles trapezoid. We'll talk more about that in the future. That would also imply that this this trapezoid is isosceles as well, which would mean that this is also 9, because these two sides would be congruent to 2. So if I want to set up a ratio that lets me solve for x, I can note that, I guess I could set this up in different ways, but suppose I want to look at the ratio of small to big. I could say that 9 to 12, because MH, let's see, actually, UV would be the first and the last, and that corresponds with MH. So yeah, MH to UV is 9 to 12, as is HT, which I'm calling X, to VO, which is 16. So then from here, there's a couple things I could do, like you can cross multiply. If you want to make life easier, you could reduce this first, and get 3 to 4. And then if you cross multiply, you get, maybe I'll just cut to the chase here. 3 times 16 is, what is that, 48? 48 equals 4x. So x equals 12. Also, funny enough, based on the relative positions, if I were to plug this back in here, and note that this is 12, this would make x the geometric mean of these two shapes. I know nobody asked, but there it is anyway. And then the scale factor from math to you love. Well, if I start with the side length from math, which was 9, and look at its corresponding side from you love, that's 12. So reducing that ratio would give me a scale factor of 3 to 4, or 3/4. So what does that mean? How do I interpret this value of 3/4? That means that every side length from math is 3/4 of the side length from you love, which makes sense because it's smaller. It's 75% of the big one. Had I worded this backwards, had I asked what the scale factor is from you love to math, well, that would just be the reciprocal of this. That would be 4/3. And again, interpreting that would suggest that this shape is, or every side length from this shape is 4/3 the size of the smaller one, aka it's bigger than. It's like 33% bigger than. Makes sense. So if I were to, and I should also note that looking at scale and proportions and scaling is something that's important in physics and engineering and calculus and future math classes, obviously. So if I wanted to look at it in terms of modeling something, like modeling a smaller scale figurine, like in this case, I have the Leaning Tower of Pisa and then a fake version of it. See? Fake and tower. And, oh, by the way, I Googled this information to make sure that it's actually accurate about the real deal. And then I rounded a bit to make the numbers nice, but note that whatever answer we get here is actually going to be pretty accurate to the real thing in Italy. So a little fun fact. Nice to learn things. If I want to see how the fake model actually relates to the real model, and then kind of use the proportions to create scalars and find the actual values, then this is something we could do using this new tool in geometry here. What I can notice is that the ratio of height to diameter of the base, in other words, like RW to O, or sorry, height is OW. So I could say the ratio of OW to RW, for instance, is 11 to 3. And I know that these things are similar with a scale factor of 50. And KE, which is the base of the replica, is 30 centimeters. You might want to take a second to pause the video and try to solve this problem, because it's a pretty novel problem. There's a couple ways that you can do it, and I'm going to go over it in a minute, but again, like, try it. Pause it and try it for yourself. I'm going to be moving forward now, though. So again, there's a couple ways to do this. You could use the fact that they're similar first to try to find how this side corresponds to this one. You could use the height ratio of 11 to 3, or you could do the thing where you multiply by 50 first. But those are going to be our two steps, really, using this fact and this fact. And the order in which we do them doesn't really matter. So I'm going to do it like this. I absolutely should have brought a calculator with me. Because these are not going to be super small numbers, I think. But let's deal with the first bullet point first. Why not? The ratio of the height to the diameter of the base is 11 to 3. So since they're similar, if I know that that applies to the real deal, I know that it's also going to apply to the fake model, the small one, the figurine. So what I could say that the height of 11 to 3, let me actually say like this. Height to diameter, that ratio is 11 to 3. So the height to diameter ratio of the fake model is AK, whatever that is, to 30. And now if I want to solve for AK, I could do this a couple ways. I could cross multiply, that's fine. I could acknowledge that the fraction on the right seems to be the values of the fraction on the left, but multiplied by 10. So if I do the same thing with the numerator and kind of unreduce this fraction, I get that AK equals 110 centimeters. It actually is important to keep units in mind here, because I don't want to talk about like a building in terms of centimeters. That's way too many centimeters. So all right, let's note that this is 110 centimeters. What I should also note is that these two rectangles are similar to each other. So if I want to go from the smaller one to the bigger one, the scale factor of 50 tells me that I need to multiply this value by 50 in order to find its height. So the height of this thing, maybe I don't need a calculator actually, the height of this thing ends up being, no big deal, 5,500 centimeters. That's a very unreasonable way to talk about the height of a building. So what if I trim it down a bit, right? What if I convert it to meters? That makes more sense. Since we're already talking in terms of centimeters, if I want to do it in terms of meters, I just divide this by 100. And I get 55 meters, which is pretty tall. It's like 150 feet, which makes sense. So make sure that this makes sense to you. Make sure you acknowledge how we applied both of these facts. The one on the bottom, the k equals 30, is kind of like our given piece of information that we use the rest of these givens to accomplish means to an end. So, pretty standard scale problem. Here's one that's not so standard. This one's a little more algebraic. So again, I would suggest maybe pausing the video if you need to. But I'm just going to power through right now. So it's given to us that the ratio of rectangle, I guess I should say, let's assume these are rectangles, because they are. Rectangle pool is similar to rectangle gran. I don't think I actually acknowledged this, I'm sorry. This right here, this little squiggle, this is the symbol that represents similarity. I know that if I had, if I had these lines underneath, the squiggle and then an equal sign, that would imply congruence, but a weaker statement than congruence is similarity. So this is me indicating that the left polygon is similar to the one on the right, symbolically speaking. So if I want to set up a proportion here, knowing that these two things are similar to each other, what I could do is I can kind of note that the lengths are going to correspond and the widths are going to correspond of these things. So what I could do is I could set up a length to width ratio for each of these things. For the granite rectangle, length to width is 18 to 10. Easy. And if I want to look at, let's see, the length to width ratio of the pool, let's see how this relates. The length of the pool would be the 18 minus this walkway minus this walkway. So in other words, the 18 that is the granite minus the x walkway minus a second x walkway. So 18 meters minus x gives me 18 minus 2x. Similarly, with the width of this thing, like PL or EW, that's going to be the 10 from the granite minus the 1 for the walkway minus the other 1 for the walkway. So 10 minus 1 is 8. So I end up getting this proportion just by setting up ratios of corresponding pieces and noting that their proportions are going to be the same, or their ratios between the corresponding sides are going to be the same. So before I cross multiply here, let me reduce a bit. This will come out to, if I divide by 2, 9 over 5. Even here, if I divide every term by 2, every term, because there's a common factor of 2 to each of these 3 terms, I end up with 4 in the denominator, and I end up with 9 minus x in the numerator. So I can cross multiply here and get 36 equals, remember to distribute the 5 to this quantity. 5 times 9 is 45, minus 5x. Let's see, I could add 5x to each side and then subtract 36 from each side. If I subtract 36 from each side, it comes out to 9. This won't be clean, but 9 divided by 5 ends up being 1.8. So just to make sure that this checks out, if I plug in 1.8 here, let's see, this is 1.8, this is 1.8. It should be the case that EW is, oh, we already established this, 8. See, if we check our math, this actually does come out to be correct. And if I were to, again, set up ratios of corresponding sides to make sure that the length to length ratio, or the length to width ratio of one equals the length to width ratio of the other, it sure does. It ends up being just fine, and we could check this with the calculator too. But yeah, that just about concludes it. So again, the takeaway from using similar polygons is that if I know that two polygons are similar, and if I have some unknowns about some of the sides of one of those polygons, I could set up ratios involving corresponding sides with the pieces that I know in order to find the pieces that I don't know. And then we can use all of those earlier Chapter 6 skills involving solving proportions to get it done. Thanks again for tuning in, folks.